All right. Hi, welcome back. This week we're going to be talking about line integrals and Ampere's law. So, yeah, let's just get right into it. If you haven't seen line integrals before, this is just going to be like a basic overview. Obviously, when you take Calc 3, or if you're in Calc 3 right now, maybe you've already seen it. But yeah, this is just going to be a kind of what we're just going to need for this class, and just a brief overview of line integrals. So line integrals have a form that looks similar to this. So you have the integral symbol, and then you have something that looks like this. So in this case, f is a vector function or vector field, as you'll hear it in Calc 3. And then dot ds. So this is a dot product in the integrand. So let me just highlight that. So that's a dot product. And so what this is talking about is, so when you think of a normal integral, you think of some function that looks like this, right? And you want to find the area under this curve, right? So you want to find this right there. But with line integrals, we want to go a step further, and we want to kind of imagine this like line, hence line integrals. And we want to see how much of this vector function is on this line, essentially. So when we think of a dot product, we want to think of parallel lines, because we're looking at cosine. We want to think about parallel lines, because another way we can write this, if we were just going to isolate this part right here, so if we just imagine f dot ds just outside of the integral, we could rewrite this as the magnitude of f, the magnitude of ds, cosine theta, where theta is the angle between these two. And so most of the time when we're going to see line integrals in this class, we're going to be assuming, and actually we're going to be making sure that our line that we're working on is it is going to be in the same direction as our vector field, or in this case, it's going to be our magnetic field. And so this manifests in a few different ways. So first of all, this ds is a vector, and so it therefore has a direction for it. So if we're looking at this line right here and we want to find a particular ds, we would say it looks something like this, and it has a direction with it. And then our f can be anything. It has some relationship with that ds. But most of the time, we're going to have to be figuring out what our ds is before we do our calculation. So one way that this can happen is if we have let's say we want to find the line integral of a circle. So let's say I have, actually, no, let's start with something easier. Let's start with just a line. So let's say it starts here. This is L, and we want to find DL, which is a very valid function to write. So we want to find the integral of this DL. So I'm going to create just a small sliver DL, and it's going to be going in that direction. And I want to integrate over all of these DLs from 0 to L. And this is just L, because if we take an infinitesimally small amount of DLs and we integrate over all of the DLs from 0 to L, you just get L. So And it's going in, if we make our little axis and say this is the X direction, we would say that it's in the X hat direction. This is a vector quantity. So when you're doing line integrals, it's important to recognize that these are vectors that you're working with. So that's one way we can do it. We have a line and we want to find the line integral of a line. That's pretty straightforward. But what about a circle? So we have, let's say we have this circle. And I'm going to make, so what if we wanted to find the line integral of this? Well, there's a few problems. Let's say that this has radius r. So now we have to figure out what this DL is. And so if we're looking at our circle, we see that it goes around and it starts, let's say it starts right here on the positive x-axis, at x-axis, makes a circle and comes back to that same point. So in this case, even though I didn't actually close it, this is going to be a closed loop integral. So that's what that symbol means. If you see a integral symbol with just a circle between it, that means it's closed, a closed loop. So we see that no matter where we travel on this circle, our radius is the same. So I'm going to write that down. R is constant. So the only thing that is changing as we move across this circle is what angle we're at with the with respect to the origin. So if we say that that's the origin. And so what this DL actually is the arc length of a circle. And so if you remember the arc length of a circle, we normally call it S, is r theta. And so I'm going to change this to L just so that we're not getting confused, but it means the same thing. So the arc length across a circle is defined as r theta. So if we wanted to look at a infinitesimally small ds, or dl in this case, it's going in that direction. And let's say that it has this angle d theta. I'm going to actually draw this in a different way. So let's say we want to find this DL right here, and it's going in that direction, DL. And let's say that it has this d theta right there. Let's say it has that d theta right there, because it's an infinitesimally small DL. So what this actually is saying, if we look at this equation right here, is that our DL is actually r d theta. If we differentiate the DL, our r is not changing, but our theta is, so it's d theta. So if we want to find this closed loop integral of DL, we need some bounds first. So let's actually rewrite this first. So closed loop integral of r d theta. So now we need to know what our bounds are. Well, we see that our r is staying the same, so we're not integrating from 0 to r, but our d theta is changing, and we're starting here, so let's call this 0, and we're ending back at the same one, which is 2 pi. We go around once, it's 2 pi. So we're going from 0 to 2 pi. Our r comes out of the integral because it's constant. And we're left with d theta. And now we can just integrate this like normally. So we're left with r theta from 0 to 2 pi. And that is just 2 pi r, which is the circumference of a circle. So we kind of just defined what the circumference of a circle is. But what if, okay, so what if, so, but an important thing to note is I chose that our line integral was starting at 0 to 2 pi. But we have to keep in mind that it is also equally like easy to say that we start at 2 pi and go to 0, or we could say that I start here or here and make a loop. We're going to get the same answer, but the direction matters. So that is one important thing. Direction matters. And so that's really important, that our direction of this DL matters, because it could be, we could be going from 2 pi to 0 or 0 to 2 pi. In this case, in whatever case, if we went from 2 pi to 0, then we would end up with a negative 2 pi r. So direction does matter with how we are doing our integrals. So you're going to be seeing line integrals in Ampere's law, which basically says that the line integral for some magnetic field B dot ds is equal to mu naught I enclosed. And so this I enclosed is talking about an Amperian loop. So just like we had a Gaussian surface, and that was a surface integral, we have an Amperian loop that is related to a line integral. So it's important to recognize that this Amperian loop, or just line integrals in general, are not surfaces. They are not looking at an area. They are looking at a line, just the line. And how the vector field along that line is changing. And that's why we want to look at this for magnetic fields. So yeah, the next one that I'm going to be talking about is a problem with Ampere's law. So just stay tuned for that. I hope this was helpful. And yeah,